Hello. My name is Francis. I look like this most places on the internet. And I work at Bustle. VP of Engineering at Bustle. And so we are a content site. We're a digital media company. And a lot of people ask, hey, Francis, how did everyone at Bustle make the website so fast? And I know this one. You know, we put everything in Redis. And since that's not a talk, and it usually doesn't explain anything, I did make this talk. And I call it We Live in Memory, because it's a really nice way to say we use Redis. And I'm going to tell you about how we use Amazon Lambda and GraphQL and Redis to make really fast APIs. If you want to follow along, if you want any of the links, any of the open source, you can get the talks on the slide here. And just to prove, that we really do have fast APIs, I say 70 milliseconds in the title, because that's the average, but most requests are in 24 milliseconds. And this is our API response rate, and I love it. It makes me so happy. And if you're a stats nerd, you'll notice the distribution there isn't a quite perfect distribution, and that bothers me too, and I don't know why. So this talk's going to be in 3 parts. I'm going to tell you what Bustle is doing. I'm going to tell you how we're doing it, and then I'm going to tell you how you can do it. So we're, as I said, we're a digital media company, right? So we have big websites, and we show ads, and we do all that kind of stuff. We're one of the largest publishers for millennial women, right? And I found out we're actually just really big in general. We're bigger than the Washington Post, and they make news. And we're also bigger than Stack Exchange, which is also really weird, because that in my head is just one of the most massive websites out there. And then also doing research, I found out that WebMD is a digital media site. We're bigger than them, but the fact they're a digital media site instead of maybe I don't know, a medical site, it makes me really, I don't know. And we're growing, right? So we keep adding new sites to our platform, and it means we just got to keep being able to go faster and store more data. So what are our goals, right? We want to have the best reader experience, right? And we want to have the best features so we can make the most interesting, compelling content. And there is not a software project out there that doesn't have these same goals. They just want to be good, right? Our strategies to make this happen is we want a very fast page load. We have ads to show you, and we want to make it really cheap to change things and throw stuff away and try out new ideas. So before I go much further, I just want to say what Amazon Lambda is, because it's really easy to assume everybody knows it except you. It's functions as a service. And what does that even mean? It means you get an API, in this case an Amazon HTTPS API, right, that lets you execute your JavaScript or a couple other languages function remotely. And it lets you do it with a consistent environment, right? So you have guaranteed CPU, guaranteed memory. And it doesn't care if you have 1 running every second or 100,000 running every second. You're guaranteed to have just as much memory and CPU available to every request. And this makes scaling easier, right? And we're using it because we were able to take a whole bunch of app servers that we had there to handle push notifications and unpredictable traffic. We're paying about $30K a month, and now we're paying $3K a month, in Lambda. And sometimes we have 15, 20x our normal traffic for 2 minutes. And that sucks. Well, I mean, that's hard, I should say. It's actually really amazing. And over the time since we've been building this platform for 2 years in this incarnation or so, and we've grown about 10 times in that amount, and I haven't had to worry about it. It's still the same functions, doing the same stuff. I just got to make sure the database can stay up to speed. And I will have to worry about it soon, but it's bought us a lot. So how does it actually work, right? It works like this. So when you go and upload this article on why your kid wants to hear Goodnight Moon again, it hits our CDN. And the CDN will give you the rendered content, or if you already have the page loaded and it's an API request, go straight to the API. We render everything in React. All our API is handled by GraphQL, and all the data comes from Redis and Elasticsearch. And you can sort of split this up into a few layers: the CDN layer, the rendering layer, the API layer, the database layer. And the CDN tries really hard not to bother anyone else with anything. If it can serve your request, the CDN servers are much closer to where you live. You know, they're all around the world. And I would rather everything to be served out of the CDN. I would rather be 100% CDN served site. But, you know, there's a couple options you can use, especially if the stack. Right now we're using Fastly. But I actually have one more requirement I want out of my CDN, is that it should execute my functions. Now, this is weird because a function execution isn't exactly an HTTP request. And, but it's close enough, and it can give the same data an HTTP request can. And so in this world where I don't actually have any web servers, I don't want to have an upstream web server. I want to have, you know, the CDN do all the work. And so we accomplished this kind of hacky. We have API Gateway, which is Amazon's web server for functions. And that executes our Lambda, and then we have Fastly in front of it. And Fastly gives us really fast cache and validation, so when we update a post, it's pushed out to all the CDN in under a minute. Usually under a second, actually. There's a near future where maybe we use Cloudflare workers, where they have a V8 running in the edge, or we use CloudFront with their Lambda at the edge, and have these execute our functions for us. And that way we can drop a whole hop about 10 or 15 milliseconds, and you know, we can serve up stuff that much faster. Still an experimentation, but I think this is something CDNs are going to do out of the box pretty soon. The rendering layer, you know, so this is a function, right? And it gives us a status, a body, and headers. And that's everything you need for an HTTP response. You know, it's got a couple of responsibilities. Like, this is the app of Bustle. You know, we're all client-side apps. And so it's got to do the server-side rendering. It's got to serve up all the assets in a good way. It's got to you know, be smart about the components and the style sheets and break it all apart. And so, you know, we use React for our CMSs. We use Preact because it's not much smaller for when you go to bustle.com or romper.com. And Webpack makes everything possible. We even Webpack the API. We're happy with how that works. The API's got a couple of responsibilities. It wants to take a query and return some data, you know, and then when you want to make a change, you know, take some input, change the state, and then return some data. And I have the requirement that I want it to be strict. I want it to guarantee that when you ask for a field, you know what you're getting, and you always get it. And so we use GraphQL, right? Because GraphQL does all these things. We're able to, we used to have like a dozen microservices, and so whenever we wanted to make a request, we'd have to go and get it from one and the other, and then try to get them all back. And then sometimes, if we didn't implement it right, status codes would be different, you know, errors would be a different shape. We had a lot of ifs in our response handling to try to normalize it. In fact, our front-end team did more data normalization than our API team. And GraphQL kind of gave us a single place, a single endpoint, where we put everything behind one thing. And we wrap all our third-party services and stuff in this too. It's helped a lot to have one way to do things. And the last layer is the database layer. And you just want it to store data safely, right? And you want it to retrieve data fast. And I want it to retrieve data fast in a consistent time. Because it doesn't help me if I ask for a post and I get it in under 70 milliseconds, and then I ask for it again later and I get it in a second and a half. Like, I think that's broken. You know, I want it to be much, much faster. And so actually, it could even be slow if I know how fast it is. And in order to get this, we use Redis as our primary data store. So if you don't know Redis, it's a data structure server. And this gives you things like hashes and sorted sets and lets you talk to it over the network. Lets you do kind of operations on the stuff in memory. And a lot of people use this for cache. Maybe they put their sessions in there because they could have sort of a little JSON session in there and it's really fast and it gives it back. But if Redis dies, you know, if the process exits, all the data's gone, and you know what? That's okay. But just because it's good at that doesn't mean it's actually not good as a database. It's got known persistence. And most people, when they hear we use it, they don't know that, because why would you turn it on if it's ephemeral data, right? And so I tell them, and they don't believe me. So I'm going to show you. Whenever a write comes in, it gets appended to this append-only file, which is a lot of databases have this kind of thing. This is the write log, you know? And every second we write this to disk. So if the process itself crashes, which we haven't ever had happen in 4 years, but it can, we can just start it up again. It'll pick up where it left off. It has to load everything back in memory, and we're fine. We take that, throw it to S3, but we also take a full shot of memory, which is a little faster to load. That's the RDB, the Redis database file. And we put that to S3 too. And so we can restore another machine. We restore staging every night off that data. And, and we just have as much, I haven't had as good data retention in Postgres or anything else. I mean, and that's the fault of our ops. That's the fault of our ops. You can do this with pretty much any database. Of course, we have high availability. There are read replicas in the primary, so if it does exit, readers won't notice. Maybe we'll lose a couple of requests while it switches over. And that's fine. And this works very well for us, And you can do this with your tool of choice. This talk, I love Redis, and I would love to actually give an entire Redis talk. But this really could be any database. Whatever your favorite is, it will work just fine. So if we take our stack and we split it up into the layers, the CDN tries to do everything it can not to bother anyone. The rendering gives you the rendered content. The API, well forms and handles all the changes to state, and the database keeps everything safe. We're going to talk about this part, because this part is the part I know the most. I'm not going to talk about Elasticsearch, but we use it, for search. And we also related content and some other nice things. It's great, but in the end of the day, Redis is the primary. So let's make an example. I recently became a dad, and so all my shoes are dad shoes. And so I heard it's actually hard to pull off dad shoes. And so I was like, well, let's check it out. And at the top of Google, there's a Bustle article about dad shoes. And it turns out the secret to dad shoes is wearing a flowy skirt. But if you look at the data that goes into this post, you have what you would expect. It's a JSON blob, right? And we have sort of this tree of data. We have the site, it's Bustle. It has a post on the post field, and it has all the data for the post. And the post has an author field that has a user object. And it has a tags field, which has an array of tags. And this matches our GraphQL query real closely. We are asking for this in the same shape. And there's a little bit of prescription here because we can ask for it like this, we get it like this, and we use it like this. But if we got it back, one request for each tag, or even if nested data, if we got it back in a flat format, like with, say, JSON API or something, we would basically go and build the shape again, to give it to our components. So we've been very happy with this. You also get only the fields you ask for, so we can, on the API team, just keep throwing stuff in there for people to try out, and when they stop using it, they do. We can deprecate fields, and it pops up in their linter, and they say, oh, don't use this field anymore. And it's kind of cool. And if we remove all the data, we end up with this little tree, right? A graph, perhaps, of the names of the types and their IDs and their relationships, right? And if we squint, and we can make it kind of look like this. Right? So this site has a post field with the post, and it has the author field with the user, and the tags with the tags. And if we want to describe this in a little more graph databasey, and the graph community uses the word predicate to describe an edge. I looked it up on Google. I don't know why. I'm sorry. But the predicates here, site has post, and get a little more descriptive with them. And so we can store this in the database like we want to represent it. And in order to do that, we built a graph database. We call it Gradius, after an old video game. And this is actually the name of our whole API in the graph database. It kind of came hand in hand. And this has allowed us to grow with a relatively small engineering team. We're less than 15 people. Over the past couple of years, I don't think we could have done it without this. So whenever I say graph database, immediately people say, oh, like Neo4j, right? And exactly like Neo4j, except it doesn't do anything Neo4j does. Neo4j is amazing. It's very complicated, actually. I have a hard time, and this is a failing of mine, not it, because they have wonderful, beautiful tools that I wish I had. But it's hard for me to understand. It does a lot, and the queries can get super complex, right? And the reason ours is faster is because we made some trade-offs. But I mean, when people say databases are faster, right? What do they mean? I had a DBA I used to work for, and his big analogy was trains aren't slow. They have one speed. The people get it on and off, and the people are slow, right? But if there were no people, the trains would be super fast. Databases are the same. They aren't slow. The data going in and out, it's the queries that are slow. And he especially said this every single time somebody complained the databases were slow. But you can build a faster train, and that was the trade-off we made. In fact, we traded query flexibility for speed, and we made it super difficult to make a slow query. You know, and if you can't have a slow query, then everything is fast, right? Oh, I think I should say, yeah, because it's not flexible, because we can't do these complex queries, we replicate to other databases, Elasticsearch being one of them, you know, for search, but also to BigQuery for, you know, doing analytics, and for, you know, you can get a feed of all the changes, and so we're playing with different databases. You know, we have our RDBMSs for reporting, you know, but Redis remains the source of truth. So we love open source. We just had Ghost 2.0 got released. Have you ever used Ghost? That uses MobileDoc as a data storage, and we helped develop MobileDoc. That's how we store all of our posts. And so we haven't been able to open source Gradius because it's everything, and it's in no shape to be shared with other people. And so I started porting everything to something I call Nemesis DB. Nemesis is the US arcade port of the Gradius game, so I figured it was a good name for it. And it's really fast, you know, as fast as ours. And it's already got features I wish I could use in Gradius. And as soon as we get it to a certain point, I want to add Redis cluster support so we can get much bigger. I'm switching the whole company to it, and it'll be a nice little migration. But it's not done. However, I use it completely in this talk. It does everything I show you here today. And if this interests you, if you want to know how it works, please see me after. Please check it out and open many issues and light the fire for me to finish this, because I think it'll be better for everybody. So let's make a GraphQL server. We're going to go over the tools. We're going to go over what a schema is. We're going to go over how the resolvers work. And talk about the loaders. All right. This is our package JSON. The dependencies are Apollo server. I love Apollo. I wish I actually used Apollo server for Gradius. We started it before it was ready, I think, but it's totally ready now. And it's not that complex either, and that makes me happy. I think it's hard to make simple things. And so the Apollo tools and the Apollo server stuff, they've been able to help make it more straightforward to develop, and I'm very happy with it. And so our server file, and this is what you would use for developing on your own machine, reads like this. You know, you do your requires, and you get all your type definitions. It's just a file you read into a string. And then you start the server, and you say, here's the schema, here are my resolvers, and I'll listen on a port. There's not much more to it. If you have a Lambda, you know, when you deploy to Lambda, it's the same thing, except they have a slightly different server which knows how to handle the Lambda requests. And instead of listening on a port, you tell Lambda, hey, this is the name of this is the function you call for each request, and it handles the rest. But what it gives you is a lot. So you have it can process GraphQL queries, but it also gives you GraphQL, which is a tool that you can use to play with queries, right? And so forgive me, some GraphQLs are white, some are black, some are dark. I don't know how easy this is to read, but this is a query on the left and the data on the right, and a big play button in the middle. And so you can get auto-completing queries where you can hover and see which type it's supposed to be, and then see the data it's going to get, copy and paste this into your component, and use it. And even better, it's documenting, because the schema isn't just for the GraphQL server, it's for the client too. And it's able to pull out all the relationships. So this is the site, which has a post, which has an author, which is a user, you know, and you can see what all the types are, you know, you can see if they're going to be null or not, and you can click around, and if I wrote descriptions, which I didn't, you'd see them there too. If I wrote deprecations, which I didn't, you could see why we got rid of stuff. And I firmly, GitHub's GraphQL API is a wonderful shining example of how you can do this right. You know, we crib stuff from them quite a lot. So the schema defines what the data looks like, and it doesn't care how it works. So I have the site, and I have the posts and the users, but all it cares is what's the data going to look like when you give it to the API client. It doesn't care where it actually comes from. And so the only thing required is the query, right? And here we have a field called site, and the site requires a name, which is an enum, so you don't have to put it in quotes, and it can only be specific things. And it returns a side object, guaranteed. That's what the exclamation point means. It means not null. And the site itself has two different kinds of things. It's got some data, the ID and name, right? And that comes from our database. And then it's got this lookup field, post. And post takes the required path, it's a string, and it will try to give you a post. It's maybe give you a post. It's not null. Or rather, it is nullable. So it doesn't know, for sure that there is a post at that path. And that's OK. Neither do we. But there's no difference here between data and lookup fields. And that comes later in the resolvers. Post is another example. You have ID, path, title, body. Those are all data. They're just strings and numbers. They could be objects, but they're data. And the authors is a lookup for the user. The tags is a lookup for the tags. And we guarantee to give you an array, and that array is guaranteed to have 0 or more tags in it. So if there is anything in the array, it's going to be a tag, but there doesn't have to be anything. And if you've used a typed language, or if you're TypeScript, you'll notice that there's no way you can type the length of an array. And users and tags are boring. They're just data. So that's great. So the resolvers, you don't need a resolver for everything, just for the lookups, right? And this is where it kind of gets this is where the infinite power and variability, of how a million ways you can do things sort of is a paralyzing force when you're starting with GraphQL. But it just needs to return full objects of other things. This is you can do many things, but this is the most common case. And you do it per type. So our query has the site field, and so it gets a function, and it gives you the root is nothing in the query case, but the argument object for the second one, if you recall, site required a name. The site has the post field, and if you recall, it requires a path. But it also gives you the site as the root of that lookup field. And the post itself, you get the post, and there are no fields on those lookups. And so using that post, you have to look up the authors, and you have to look up the tags. And in practice, we do it like this. So this is the site looking up its post. And so Nemesis DB has something called a labeled edge, but it just means you can, on the site store a path and have it be a reference to another object. And so we look it up, and if it doesn't exist, we return null, which is perfectly allowed by the schema. And then we have, and then if it does exist, we go and we find it and we return that object. In fact, we return a promise for that object, which is just fine. Post is a little more complex, but the author, well, actually, each one is even more simple. The author looks for an edge to a user, and it returns it. It pulls out the ID and then actually goes and gets the user. Same thing for the tags, except it's an array, so we get all the edges for the tags, and then we just sort of map over and get each one, return it in a promise all. And so this each returns the object you're looking for. Now, if you have ever worked in, say, Rails, the concept of n+1 comes up all the time. And this is when you're making too many round trips to the database, and it slows everything down. And it's really just not a problem if you batch the commands, batch the queries, right? And so data loader is a little utility. It's like a couple hundred lines, and it lets you take all the requests you make in one event loop and batch them all together. So you give it a little function to do the lookup, and I made up a function here, get a bunch of IDs, that knows how to look up like a whole array of IDs. And so you can go and ask for a bunch of objects, and then it's going to call your batch loader, your get bunch of IDs, with a deduped array of all those things you're trying to get. And this allows you to, instead of having, if I load 50 posts and all their authors, instead of loading each author individually, it's going to go and give me 50 IDs for those 50 authors. So instead of doing a new request, a new lookup to the database for each item, it does it for each depth of the graph. And this made it much faster. And we were able to abuse this a little bit, and we were able to do it with Redis itself. There's something called pipelining, which lets you put a whole bunch of queries together into one query and send them all. And so if we wanted to, this is Nemesis DB again, which can take a Redis object, or it can take a Redis loader object, which is the same shape. And if you go and you ask for all these nodes at the same time with Redis, and this is not a fair benchmark, I ran it on my own machine on localhost, but it will do 4 different queries. But with Redis loader, it does 1 query with less, because it doesn't ask for node twice, and it's significantly faster. When you add a real network in there, maybe you need to multiply this by 10 or 100, but it's still real fast. So even if we didn't batch, I don't think I would have noticed for our setup. But for most databases, which maybe it's a couple milliseconds between responses, it's a good idea to keep them together, and this keeps you protected. I guess it becomes from an n+1 to an n+1 divided by, whatever's a reasonable batch size, 200, something like that. The tooling we use to deploy our Lambdas, right now we're using SAMI, which uses Amazon's SAM, the serverless application model under the hood. But SAM is kind of annoying. SAM is kind of verbose. And so we made a little wrapper that helps generate some useful scripts. And so we use SAMI for most of our projects. I'm really excited about Architect. You can find it at arc.codes. And it lets you describe the kind of serverless environment you want, DynamoDB tables. It's a little prescriptive, but it's super straightforward to use, and I think it makes getting started with Lambda super easy. And of course, we built a tool called Shep, which I forgot to put in the description, but Shep is the shepherd for your Lambdas. And Shep is not prescriptive. It just sets up like here's your functions in a folder, here's a Webpack config that works, and we'll deploy stuff in about a second or two. And it's the fastest way to get something out there because it skips CloudFormation and all those other big things that if you don't know about yet, maybe get in the way. But it still works. It's great. We've required more, and it's easier to go to SAM, or rather SAMI. I think that's all you need to get going. I think you could take this, and if you go to the repo, I have all the code there, and you can choose one of those deploy tools, and you can run your API on Lambda today. Redis, running Redis, for a hobby project is a little more expensive, so you can swap that out for anything you want, like literally anything you want. So DynamoDB or Postgres, and it will work the same way. Nemesis isn't finished, and you can totally help. And if you have opinions, or if you think we could achieve this with a database that already exists, you should come and try to convince me of that, because it'd be awesome not to build anything. We have a ton of open source libraries that we use for our stuff. We just share them, and sometimes we sneak them into other things. But everything from the command batching to efficiently storing JSON documents of trees, to working with async iterators, which I want to completely replace all my streams with, to using async functions in streams with BlueStream, which was our workaround before async iterators was a thing. You should check it out. Love any feedback and help, and hopefully it makes working with whatever you're doing somewhat easier. Thanks.